Okay, today's topic is capacitance. Prior to watching the lecture, I invite you right now to pause and then immediately take a look at two demonstration videos that I have uploaded for you. Capacitor demonstration and also the Leyden jar demonstration. So make sure that you take a look at those two individual videos right now. Okay, now that you have seen those videos, let me explain exactly what is meant by a capacitor. This is the simplest way by which we can store electric potential energy. I'm also going to give you a short introduction to circuits here as well. Okay, so from last time when describing a chemical battery, recall the following symbol that I drew. I'm going to draw it on its side here on this diagram like so. Two lines, one larger than the other, and then we have wires going off in this direction like so. Okay, this side of the battery where you draw the larger line, that's the region of high potential. It's the positive side of the battery, if you will. And then the smaller line here, this is the region of low potential. This right here is the negative side of the battery. Okay, then the potential difference here we'll just simply label as V. Okay, and now what we're going to do is connect two wires to two pieces of metal. Right over here off to the side, and then right over here off to the side. This symbol that I'm drawing here where the two lines are the same size is the capacitor symbol. All right, now all that I really have here are two pieces of metal. There's a piece of metal here, it's a conductor. There's a piece of metal here, it's a conductor. Think of the wires going to here and a wire going to here. Okay, so if I hook up this initial circuit, what's going to happen? Well, electrons are going to get pushed, if you will, away from the negative side of the battery in this direction like so. This then means that this side of the capacitor, this plate as it's referred to as, becomes increasingly negatively charged, like so. But then the opposite happens on the top half of the diagram. This right here is the region of high potential, the positive side of the battery. So ultimately electrons get pulled in this direction like so, away from the capacitor towards the battery. Remember that electrons are negatively charged. So then therefore, this plate of the capacitor becomes increasingly positively charged, like so. As time goes on, it gets harder and harder to push electrons in this direction because this is increasingly becoming negatively charged. It gets harder and harder to pull electrons in this direction because this is increasingly becoming positively charged. In other words, work is being done by the battery in this process. The energy that is being used by the battery in this process then gets stored as electric potential energy within the capacitor. Okay, now when does the flow of electrons stop? The flow of electrons stops when the following occurs. Think of this right here as a single piece of metal. If this entire piece of metal is at the same potential, if it's at the same height, in other words, the potential difference between any 2 points within that metal is 0, this then means that the flow of electrons stops. So there's no potential difference between here and here. There's no potential difference between here and here when that process finishes. Same thing here down below. The flow of electrons will stop in this direction once this piece of metal is all at the same height, all at the same potential. So then therefore there's no potential difference between here and here on the diagram. There's no potential difference between here and here on the diagram once the flow of electrons stop. So what you end up with are two equipotential surfaces. Just think of this complicated looking diagram here as two pieces of metal. Here's a piece of metal here, and it's all at the same potential. Here's a piece of metal here, and it's all at the same potential. So the flow of electrons stops when both pieces of metal become equipotential surfaces. So the flow of electrons stops when the two pieces of metal, once again, that's the easiest way of thinking of it, each becomes an equipotential surface. So then, therefore, this then means that the voltage of the battery, the potential difference between here and here, is the same as the potential difference between the two sides of the capacitor from here to here. So we end up with the same potential difference, V. Okay, now when that happens, there is then, therefore, a charge which occurs or gathers on the plates, as I've already described. Okay, let me use some symbols here now to describe that. So this side of the capacitor becomes positively charged. There's a plus Q associated with it. This side of the capacitor here becomes negatively charged. There's a negative Q associated with it. The amount of charge that gathers on the plates of the capacitors depends upon the voltage. The charge is proportional to the voltage. Now, what is the proportionality? The proportionality is geometry. The geometry of the plates themselves, it tells us how much charge, and then therefore how much potential energy can be stored within the capacitor. That quantity is referred to as capacitance, and we then give it the label as C. Now this is a new quantity for us, so before we go any further, let's just briefly check the units. Okay, the units of capacitance are as follows. Capacitance is charge per voltage, like so, and charge is in terms of Coulomb, and voltage, of course, is in terms of volts. A Coulomb per volt is given its own name. It's referred to as a farad. It's named after Michael Faraday. Now here's a nice mechanical analogy for capacitance. Wrap your head around exactly what is being described here. A nice analogy to use is that capacitance is similar to a gas tank. Let's say, for example, that you're trying to fill up a gas tank. How much gas you could cram into the tank, first of all, depends upon the air pressure that you're using. Think of that as the voltage. But then the amount of air that you can cram into the tank doesn't just depend upon the air pressure, it also depends upon the geometry of the tank itself. Its size, its volume, its area, and so on and so forth. That's what the capacitance is. Think of the capacitance as a tank. It's not a tank that's storing air. In this case, it's storing charge. It depends upon its area and also the separation between the two plates themselves. Okay, now on this same diagram, this right here was the positive side and this was the negative side. So then therefore, once the capacitor is charged up, as we say, there is an electric field that is present. And then the two plates here are separated by a distance d, and then the plates themselves have an area A associated with them. The bigger the area, it's like the bigger your gas tank, the greater the capacitance. In other words, the more charge, and then therefore the greater amount of potential energy that can be stored. In other words, capacitance is proportional to area. However, the closer that the plates are to each other, this then also increases the capacitance as well. The reason for this is because ultimately the electric field is strengthened when you have the two sides of the capacitor's plates as close to each other as possible. So then therefore the capacitance is inversely proportional to the distance d. So if you make the distance d, for example, really small, then the capacitance is large. Therefore you can store more charge, therefore you can store more energy. If you make the capacitor's plates really large, the area A is big, then therefore it's like increasing the size of your gas tank, then you can then go ahead and store more potential energy in that manner. Now in my opening demonstration video, hopefully you watched it already, I used that blue cylindrical capacitor to ultimately get it charged up, and then I discharged that capacitor through an electric motor. If you could take that blue capacitor and cut it open, here's what you would see inside. Okay, you would not see the capacitor shaped like the basic symbol that we use on the diagram above. Instead, you would see it shaped in this manner. here is one capacitor plate, a single piece of metal. And then separated from that is another piece of metal, another capacitor plate, like so. Like this. So there are actually two pieces of metal there, first in purple and then secondly in red. Notice that they are curled up in this manner such that the area of each one is huge. So if the area is big, then the capacitance is big. We can store more potential energy. Also, the two plates themselves, red and purple, are really close together. So then therefore the distance d is small, and then therefore the capacitance is large. So in typical capacitors, we construct them in this cylindrical manner in order to make the capacitance as large as possible. Okay, this right here concludes part 1 of today's lecture. I'm going to go ahead and pause the video here, and then I'm going to set up for you a part 2.